Hello and welcome to this presentation entitled Solving First Order Differential Equations via Direct Integration and the Separation of Variables. What exactly are we talking about here? Remember, we've seen and learned what differential equations are and what they represent. Now our task is to start on a journey of learning different methods of solving differential equations. So in this case, we're going to start at the simplest level where almost everybody knows everything. For example, we're going to look at differential equations of this form. First equation here is the first derivative, and the right hand side is simply a function of x. And this side we have, instead of function of x, we've got a function of y. And the third type will be of this nature, where the first derivative actually comes as a function of two variables, and there's say p of xy, which you can also express in this way. By the end of this presentation, you must be able to solve all these types of equations. In other words, you must be able to manipulate these equations in such a way that we can proceed and land at a solution of the differential equation. You must also be able to explain what is meant by a general solution and also explain what is meant by a particular solution, and you must also understand what is meant by a family of solutions and be able to sketch a family of solutions to a given differential equation, and also determine the general solution to a given first order differential equation, and also be able to determine a particular solution to a given differential equation. Actually, the equations given above are not totally new to us, though we've seen them before but never referred them as first order differential equation. What do I mean by this? If we look at the following exercise, these are integrals which we have seen before. In this case here, we're integrating a constant minus 3 with respect to x, and here we're integrating a function of x, which is x multiplied by sine of x squared. We've seen this before, but in the context of integration. But how does this link with differential equation? First of all, looking at the first integral here, always when we're given this integral, you must understand that this meant that there exists a function of x such that its derivative, first derivative dy dx, is minus 3. So in other words, what you can see here, I've actually expressed this integral in terms of a differential equations as we saw it before. So in other words, when we're looking at this, we're looking at a differential equation, but this differential equation is equivalent to this type of an integral. So what I'm saying is that when you're dealing with indefinite integrals, we're actually dealing with first order differential equations of this form. The same applies to the second one. If with this integral, we simply mean the same thing, that there exists a y such that the derivative of that y is equals to this function. Because remember, when you're integrating, what was supposed to be the under integral sign here was supposed to be a derivative or something which can transform into a derivative. So proceeding this way, we are then concluding that when we're dealing with the indefinite integrals, we're indirectly dealing with these first order differential equation. Now let's go into this more explicitly. Now we can now look at those as differential equations, which simply, that integral was simply equivalent to saying solve the following differential equation. In this case, we've got two of them here. And now let's proceed to how did you solve this. So if we had the derivative being this, we wrote it as an integral that, and then integrating minus 3, we can use power rule there, because when we've got minus 3, we know that we've got minus 3 by x to the power 0 with respect to x. If we integrate this using power rule, we can take this constant minus 3 outside the integral and have this as minus 3 integral of x to the power 0 dx. And since our n here is 0 and is different from minus 1, we can use our power rule, which simply now is going to give us equals to minus 3 x to the power 0 plus 1 divided by 0 plus 1 plus c. Exactly what we're getting here, 3x divided by 1 plus c is the answer which you get there as an integral. But in this context now, we're looking at this y equals to minus 3x plus c as a solution to this differential equation. And in particular, because of this c which we've got here, which is not determined, whose value we don't know, then we call this solution a general solution. Now, what does this mean? It actually says that this is actually it's not one function. It is actually a family of functions. In other words, for each c we get here, we're going to get a solution to that same differential equation. For example, if we take y equals to minus 3x plus 4, this is one of these members of this family represented by this expression. Similarly, if we've got y is equal to minus 3, x minus 5, you will see that this is also a solution to that. Like we saw before, you can now go on and check whether this is really a solution by grabbing the right hand side and doing that differentiation. You will see that you establish that the two of these functions are a solution, and the infinitely more functions of this form, they are a solution. So they give us a family of solutions. Now, taking that family of solutions, representing it graphically, which you must be able to do, you will see that this is a line of gradient minus 3. Now our gradient m is equal to minus 3. So all these lines, if you can see, they are parallel, so their gradient is minus 3. So what differs actually in this different solution is the point of intersection with the y-axis, which gives us those different values like 4, minus 5, and so on. So then they would have represented a family of curves which are a solution to this differential equation. I hope that is very clear. Next, moving forward, now we can actually just pick on one of them, and if we want to get only one of these functions, we actually need to give a condition like we have got here, that given that y at 0 is equal to 1, then if we substitute in this expression here, we substitute x by 0, we get an equation in terms of c, which we can establish here by solving and seeing that c is equals to 1. And then that gives us now a solution which is y is equal to minus 3x plus 1. In this case, we're going to call that a particular solution. Now, as you can see, a particular solution would be a solution which actually satisfies a given condition. In this case, you can call this an initial given condition. So we would be given a differential equation plus a condition which says y at 0 is equals to 1. So if we see an equation like that, then we must know from start that we are actually targeting to get a particular solution. But in this case, we would actually go first integrate to get the general solution, then evaluating the general solution in this way, we then establish what is C, then we write the particular solution. I hope the process is clear. In this case, one should emphasize that this particular solution is actually unique, like I highlighted here, is a unique solution, meaning it's one and the only one which satisfies this condition. As I mean that there are no two particular solutions which will satisfy a one condition given, like say y at 0 is equal to 1. So this will be a unique solution. By unique, we simply mean one and the only one. Now moving forward, we can now look at this following differential equation. So like we said before, this differential equation is equivalent to this integral. But now because we're looking at solution, we write that integral as y is the solution is equal to the integral of this expression. So when we do this method we've been using from the first example, we actually call this solving the differential equation by direct integration. Because what we do actually, we just simply convert the differential equation into its equivalent integral form, then integrate. We call that direct integration. So now the solution here will be y equals to the integral of x sine x squared dx. So then we apply our knowledge here that what is under integral sign here, if we have to solve this using analytic methods, it must be a function which is a derivative or at least transformable to a derivative. So we can use this method of substitution here by saying let u be equals to x squared. And then our du dx will be equals to 2x using power rule. And then we'll see that we can now write du equals to 2x dx. But note that when we get to this form, this is appearing integral in the integral here is that and that. And now since we're changing the variable from x to u, so then which means we must find an expression of u with which to substitute these two factors here. So simplest thing you can do here, you divide both sides by 2, then you get du over 2 equals to x dx. In that case now, we have got an expression in terms of u to substitute these two factors here. So then we come here and now write the integral in terms of u, which will be simply sine u du over 2. That's our immediate substitution after that. So we can see that now we've got a constant here, 1 over 2, which you can filter outside to outside the integral and write that as half integral of sine u du. And in this case, we all know that sine is not an immediate derivative of a function, but minus sign is. So we actually wish that there was minus sign here, but we actually got plus sign. So in this case, we know that if we've got a plus sign, we should have got it from a combination of a minus and a minus. So what you can do here is simply to write half minus 1 times minus 1 sine u du. You can check that these two are equivalent because it's just taken here the sign in terms of talking about plus and minus of sign is a plus. So we're changing it to two minuses, which is equivalent to a plus. Then our target is to transform what is underneath here to be a derivative. So what we're going to do, we're going to filter out 1 minus 1 here outside and get minus half over 2. And then under integral, we're going to get minus sine u in brackets du. Then we've got a derivative here. And we know that the derivative minus sign is a derivative of cosine. Then you simply say here equals to minus cosine u all over 2 plus c. So the integration is over. That variable u was simply used to help us manipulate this integral easily, and we have arrived there. So now, to conclude, now we can simply say now y is equal to, remember y is a function of x because here we're giving integral of x. So now we just come and do backward substitution here and write this as minus cos x squared, which is equivalent to u all over 2 plus c. So again there we've got our general solution. Since we're not given an initial condition, we can simply leave this as a general solution. Then the next types of integral we're going to look at is this one, which in this case now the right hand side of the function is actually a function of y. So I'm going to pick any of these functions and solve it at example. The rest I'm leaving them for you for practice. So let's say solution. In this case, I'm going to pick part 4, which I'm just saying solution to part 4. So what we're going to do now, you can see that we've got here dy dx equals to a function of y, which is cos squared y. So if we were to do direct integration, you cannot do it, you cannot apply it in this form. Because if we integrate both sides, here we would expect to integrate this function back to y, but there is y this side, there is y that side. So we do some kind of rearranging this variable. In other words, that on one side we've got terms of y, and on the other side we've got terms consisting of variable x. So what you can simply do here, you can rewrite this equivalent by dividing both sides by cos squared y. You would write this as dy over cos squared y dx equals to 1. We are still not ready to do that. So to apply integration, so what you can do, we can simply now here multiply both sides by dx. Then immediately then we're going to have something like dy. Actually there we've got a y over cos squared, which is actually sec squared y, writing it simply using identities, equals to dx. If we look at that stage there, we've got variables separated, and then we've got here expressions of y and that side expression of x. So immediately we can apply direct integration on both sides, whereby we can apply the integral sign here as sec squared y dy. And on the other hand, we apply the integral sign to dx. And we're actually ready to integrate because what we have here in the sign is actual derivative. Sec squared is a derivative of tan y. And this side we've got x to the power 0. Applying power rule again, we can simply get x plus c. I hope you noted this point that I've added c only on one side, in the side of x, where x actually is the independent variable of y. Y is dependent here and x is independent variable. So I advise you that please don't be redundant or do something redundant by adding c's on both sides. Just add c on one side. So now if we were to, what we have here, we have got to our solution y given implicitly. So to give it explicitly, I think you see that we can apply the inverse tan function on both sides. And then if we do that here, we're going to get y, and then this side is going to be tan of the independent variable x plus c. Then we've got a solution. Recommendation again. Please, whenever it's possible to leave y as an explicit function, do that. But sometimes you get some situations where it's not possible to leave y as an explicit function, then you can simply leave it as an implicit function. So there now, we've got our general solution. I'll just write general solution. That's for general solution. Then moving forward, this is we have actually answered this question. We've got the solution y. You've seen what you can do there. So what is left for you to do now is to proceed and solve the rest of examples which remain here and make sure you practice. There are 3 of them, from the easiest actually, bit by bit, they become more complicated. And I hope you're going to realize that when you get to this exercise here, somehow, you're going to need to use partial fractions, which you are expected to know. And then let's come to the last form of the differential equation we gave at the beginning. So in this case now we've got the first derivative dy dx. Please know that always when you're given a derivative like this, you must always know that here we've got a dependent variable and here we've got the independent variable. So the function we're going to get here is simply going to be y, which is going to be an expression of x. That's what this is actually how we must read this. But in this case here, what we are being told here is that this function can be expressed this way as f of x multiplied by g of y. What actually we see when you look at this expression is the following, is that the right hand side, the p of xy, is factorizable to two factors which are f and g, each one of them a function of single variable xy respectively. And then we shall call these types of equations of separable variables. So whenever we see a function whereby the right hand side can be factorized into two factors, each one of the factors a function of one variable, we'll say that equation is an equation of separable variables. In this case, there are examples of equations which we should look at carefully and see how we can solve them by separating variables. This is the equation of separable variables. In this case, again, I'm going to choose one example and solve it, and then you are going to solve the rest. So I think I'm going to pick again example number 4 here. There it is. So now, if we're suspecting that this is an equation of separable variables, then we must find a way of expressing this expression of x and y as in this form. In other words, in the factorized form, one factor being a function of x and the other being a function of y. So this is what we're going to do. I think you can see here that there's a common factor e to the power minus y, because this term here, e to the power x squared minus y, you can simply write it as e to the power of x squared multiplied by e to the power minus y. You want, for these kind of problems, your manipulation skills using algebra are going to be very, very important. So in this case, once I've written this like this, I think you can see that I can draw out e to the power minus y here as a common factor. Then I write this as follows. It's going to be e to the power minus y. In brackets, we'll have x e to the power of x squared plus 2x. That's that. So now we can see, remember, multiplication does not worry about the order of factors. So what we've got here, we've got fx multiplied by g of y. So separation of variables now, it means exactly to organize this equation in such a way that on one side you have a packet of in terms of y, and on the other side of the equal sign you have got an expression in terms of x, and they must be equal. Then after that, what you do, you go back and resort to direct integration of both sides. So in this case here, the easiest route is to divide both sides by, or let's say, if you don't want to talk about division, we can say let's multiply both sides by dx over e to the power minus y. So if we do that, we can see that on this side we have e to the power y divided by e to the power 1, which will give us 1. Then we're left with x e to the power of x squared plus 2x brackets multiplied by dx. On this side, dx is going to simplify with dx, simplify into a 1, and then this is going to remain as e to the power y dy. I hope you understand why. Now I end up with y instead of minus y. It's just the same properties of indices. If I've got 1 over x to the power n, this is x to the power minus n. So that's exactly what I've done. So once we've done that, we can now apply integration on both sides. Sometimes we can actually even go to the extent not even writing integral sign, but simple saying, if I integrate both sides here, I'm going to get e to the power of y. Why? Because I've got a derivative here. I've got e to the power of y multiplied by the derivative of y, which means I've got the structure of a derivative of an exponential function, because we know that when you differentiate, the exponential function comes back exactly as it is multiplied by the derivative of its argument. So the argument is y here. So it's e to the power y multiplied by the derivative of the argument. So that is the derivative of e to the power. Then when you come this side, you can see that we can actually, maybe here, because we need a lot of multiplication, let me put an integral sign here, which is going to be x e to the power x squared multiplied by dx plus integral 2x dx. So then here, I think we're going to apply the same trick we multiplied before. If it's derivative, this is the derivative of exponential function, we will have the derivative of argument, which is actually derivative of argument here with derivative of x squared with respect to x. That will gives us 2x, which means here we are short of a 2. But we've got a 2 because we've got a 1, and the 1 is simply equals to 2 over 2, expressed explicitly as a rational number. So now if we do that, then our next step will be writing this as 2 over 2 x e to the power of x squared dx plus integral of 2 x dx. So now here we can filter out half, and then we remain with 2x, which is the derivative of this exponential function. Then we'll simply write this as e to the power of x squared over 2 plus 2x to the power 2 divided by 2, applying power rule to this, plus a c. Then our integration task is done. Now what we can do is just to simplify this problem. So let's just write something here and say e to the power y equals to e to the power x squared divided by 2 plus x squared plus c. Now we can see here y is given implicitly, but we can leave y as an explicit function. Simple thing to do is to apply the inverse function to e, which is ln. Then when you apply it here, we simply get y. Then you get this as the ln of e to the power of x squared divided by 2 plus x squared plus c. And I put that in brackets because ln does not accept negative arguments. So this is absolute value of this expression. So at that point now, we have found again the general solution of the equation which we're looking at. So at this point, I think we've seen how we can solve the three types of differential equations I gave at the end. So what is left now is to take the examples which I left for you and engage them and practice and get familiar to this. At this point, I would like to say thank you for listening. My name is Charles Wasfane Msipa.